Hello everyone, I'm Baxi. Today I will present our work on frequency modulation of body waves to improve performance of limbless robots. First, let's take a look at limbless robot gaits. The stereotyped limbless gaits can be interpreted as a superposition of two traveling waves, one in the horizontal plane and another one in the vertical plane. The important parameters are kappa v, the number of waves in the vertical plane, and kappa l, the number of waves in the lateral plane, and phi naught, the phase difference between two waves. One of the well-known limbless robot gaits is a Sidewinder gait. Its gait formula is that kappa v equals to kappa l and phi naught equals to pi over 2. Another documented limbless robot gait is a frequency turning gait. Its gait formula is that kappa v equals to 0.6 kappa l and phi naught equals to pi over 2. However, when we test the Sidewinder gait formula, we observe that the turning behavior emerged as we decrease the spatial wave numbers. We measure the emerged turning by the rotation per cycle, and we observe that significant body rotation only occurs for a range of gaits with fewer wave numbers. We then explore why such turning behavior would happen. We observe that when the gaits have fewer wave numbers along the body, the gaits tend to be less statically stable, as the center of mass can go outside the supporting polygon. We show an example here, where the center of mass is bounded by the supporting polygon for 1.5 waves and went outside supporting polygon for 1 wave along the body. We quantify the static stability by the fraction of a gait period that the center of mass is inside the supporting polygon. Interestingly, we observe that the range of statically unstable gait overlaps with the range of emerged turning behavior. They might suggest that the static stability is one of the reasons for the emerged turning performance. To validate this idea, we study the temporal frequency dependency of the gaits. We expect that the emerged turning behavior would vanish at higher temporal frequency, as the gained dynamic stability from the inertia can compensate for the loss of static stability. As expected, experiments suggested that at high temporal frequency, the emerged turning behavior vanished and the robot has pure translation. Similarly, for the frequency turning gait, the locomotion performance is significantly different for gaits implemented at high temporal frequency and low temporal frequency. We measure the turning angle per cycle, and we observe that this turning angle per cycle is temporal frequency dependent in both Sidewinder gait and frequency turning gaits. We then propose to stabilize the statically unstable gait by modulating the vertical waves. We observe that increase the wave number in the vertical plane can change the contact pattern distribution and therefore stabilize the gait. We use geometry mechanics to find phi naught to coordinate the lateral wave and the vertical wave to produce a motion in our desired direction. We summarize our gait stabilization procedures by the algorithms shown here. As a result, we show that turning performance vanished in the stabilized Sidewinder gait in both high temporal frequency and low temporal frequency. Similarly, in statically stable frequency turning gaits, the turning performance is robust over temporal frequency. We quantify our observations as the figure shows. The rotation per cycle for statically stable gait is then independent of the temporal frequency. To summarize, our project expands the limbless robot gait family and expand the gait formula for the Sidewinder gaits and frequency turning gaits. We also test the effect of static stability in robot implementation. Our experiments can throw insight into stabilization algorithms for more morphologically complicated robots. That is our presentation for today. Thank you.